progress.
Hi everybody, in this next set of videos, we're going to look at applications of trig functions. And we've seen a couple already, but it's just kind of a nice section to go through multiple applications so you can see how trig functions really can be used. And the ones that you see here are just obviously a few examples. As a little side note, my husband is actually a carpenter. And he uses trig functions pretty much every single day in his line of work. So we often joke, or I joke with him, that he does more math in the day sometimes than I do, even though I teach mathematics. And trig is something that he really uses all the time. And also things like the Pythagorean theorem when using triangles. So just a little side note there, something fun, because you never know what you end up doing in life, right? I know he did not start out thinking he was going to be a carpenter. He started in college going for history and ended up changing a little bit later on after that. So just a little side note there for you. So we'll do some examples here, but do note that, of course, there are lots of applications here of trig functions, particularly in things like construction, carpentry, things with boats, building, etc. So to start, I just have a basic triangle here, meaning that there's no real application background yet, just to show you the skill that we're going to use, and then I'll give you some applications from your text. So this first one here, we have kind of a partial right triangle. It is a right triangle, so this angle is 90 degrees. And we know one of the lengths of the sides, and we know one of the angles, but we don't have everything else. So it's asking us to really solve this right triangle, meaning fill in the missing pieces. So what's the other angle? What are the two lengths there? So the angle is the first thing I'm going to start with. I'm going to actually just get out my calculator here. Use my calculator app. So remember that this is a right triangle. So this here is 90 degrees. And in our triangle, the sum is always 180 degrees. So I can find this missing angle pretty quickly. Actually, this should be C. Let's fix that. We'll call this angle B. And I can do that by using the idea that the sum is 180. So 32.5 and 90 plus that angle B must all add up to 180 degrees. If I add these together, I have 122.5. And then I subtract that from both sides. I'm just going to use my calculator here, but if you are doing it by hand, just make sure you add on that decimal point there. And I have that my angle is 57.5. And again, I'm using degrees here. So just make note of which units you're using. Here we're looking at degrees. I will say that in a lot of applications, degrees are used more than radians. I know my husband, who's a carpenter, he uses degrees. He does not use radians at work, whereas in more upper level mathematics, we tend to like to use radians. So it is good to be able to go back and forth between those two forms. So we have our other angle. And we do need to find our lengths of our sides now. And there's different ways that you can do that. So you want to use any tool that you have in your repertoire to find these answers. So you have a lot of tools now that you've seen, a lot of different formulas and ratios and things, identities already. So whatever you want to use, you can. What I'm going to note here is I'm going to start with the angle that's given, although I do know all three angles now. And I'm going to think about the fact that I know the 12.4 side, but I don't know the others. And I remember that tangent is always opposite over adjacent, right? So it's going to be opposite over adjacent. So if I start with this base angle of 32.5 degrees that I was given, well, the opposite of that would be the A length, and the adjacent would go ahead and be the B length. Yeah, remember your hypotenuse will be across from the 90 degrees. So that would not be one of the angles we're using for tangent. So it's the 12.4. And what I can do now is I can go ahead and solve that equation. So I can multiply both sides by 12.4. And I can get my approximation for A. Now, I'm definitely going to use my calculator here because tangent of 32.5 is not a common angle. I do need to check my format, though. If I go to mode, you can see my calculator was in radians because I was doing that last. I'm going to make sure I'm in degree mode here. And then I'm going to go ahead and plug this in. So I have tangent which is right here. And then I'm just going to type in 32.5. And I'm multiplying that by 12.4. And I get about 7.8996. We do want to round to 2 decimal places here. So if I look at this, that 899 is going to get bumped up. So it's going to be 7.90. And see, we have units here. We don't have units here. But whatever our units are, whether they're feet or inches or centimeters or etc., whatever they're going to be. So we have our A. Now I do need to find my C as well. And again, there's different ways you could do that. One way to do that is to now use the Pythagorean theorem, right? You could do A squared plus B squared equals C squared and solve that. Another way to do it could be to use another one of your angles. So for instance, if I think about cosine of 32.5 degrees, well, cosine is always adjacent over hypotenuse. So in this case, it would be the 12.4 over C. And again, I could solve that way to find C. So I'm going to do that way here, but you could also use that Pythagorean theorem as well. Just make sure you watch your rounding and things like that. So here I'm going to multiply by C on both sides. Again, I'm just going to, you don't really need that piece there. Multiply by C on both sides. So it's going to be C times cosine of 32.5 degrees equals 12.4. And now I'm solving for C, so I'm actually going to divide both sides of cosine of 32.5 degrees. And again, I'm going to use my calculator here. So make sure you're in degree mode. I'm going to take the 12.4 this time. I'm going to divide that by cosine of 32.5 degrees. And I get about 14.70 here as well, rounding to 2 decimal places. Right? So we're done. We have our 3 angles, right? 32.5 degrees, 90 degrees, and 57.5 degrees. And I have my 3 sides, 12.4. This one we found was about 7.90. And then this one here was 14.70. Another nice check too is just to make sure that your lengths make sense. So your hypotenuse should always be the longest side. And it is here, right? 14.7 is bigger than 12.4 and 7.9. So at least that makes sense. We're in the right direction. And it also works the same thing with your angles. So this angle was 32.5 and this one was 57.5. So what happens is the length across from the 32 should be smaller than the length across from the 57. So you also have that as a nice little check here. So, you know, your smallest length should be across from your smallest angle, and it is. That was 7.9, and then this one was the 12.4. So that's just another quick check just to make sure you're on the right pathway there. All right, so let's do an actual application problem now. And I have it already written out for us on the next page. So from a point on level ground 125 feet from the base of a tower, the angle of elevation is 57.2 degrees. And we're going to use that to approximate the height of the tower to the nearest foot. Now, if you need to write this down, pause the video, write your question down so you can get it in your notes, read through it a couple times, and when you're ready, come back. With Trig, I do highly recommend drawing pictures to understand what's happening here. So I know I have some sort of tower. I don't know what the tower looks like. I'm just going to kind of draw a tall, maybe kind of skinny building here. So I have some sort of tower. And I know that a point on level ground is 125 feet from the base of the tower. Base means the bottom. So we're going to be, you know, somewhere over here standing, and we're going to be 125 feet away. And you're on the ground. So we're taking that, that measurement from ground level there. And I know that the angle of elevation, so that goes up to the top of the tower, is this 57.2 degrees. And what I'm looking for is the height of the tower. I want to know how tall it is. So I'm looking for this length right here. We'll just call this H for height. So this problem is actually pretty similar to the last one that I gave you guys. But we actually don't need to find all sides or angles here. I really just need to find one. I just really want to find the height of that tower. So I'm looking for this, technically this side right here of that triangle, that left side. And what I could do here is think about, well, what do I know? I know an angle. I don't know the hypotenuse, right? This would be a right triangle. I know the value that's adjacent, and I need the value that's opposite. So I think about opposite and adjacent. Hopefully your brain is going to tangent there. And tangent of theta is equal to opposite over adjacent. So the tangent of 57.2 degrees is equal to whatever the opposite value is over the 125. And now I'm going to solve for h. I solve by multiplying that 125 on both sides. Right? It kind of cancels it from the right if I multiply by 125, and it brings it to the left. And then I'm going to use my calculator here. Again, we're in degree mode, so just make sure your calculator is in degree mode. I'm going to just go ahead and type in 125 times, and then I have my tangent, 57.2. I am in degree mode, so again, I checked that already. And I have that the height is about 193.962, and we're talking feet here. Now this problem wanted me to round to the nearest foot, so the height of the tower is about 194. That 9 will bump this 3 up, feet. So try to think of these like little puzzles. What do you know, right? You have a lot of tools now, a lot of formulas that you can use, a lot of identities, things like that. And look at what you have and then see what would be the best formula to use there. So here, based on the information I have, I really need the value opposite and I know the adjacent. So what relates opposite and adjacent is tangent. All right, and let's do another example. So a kite flies at a height of 30 feet when 65 feet of string is out. If the string is in a straight line, find the angle it makes with the ground. And we're going to round to the nearest 10th of a degree. So again, you want to start by drawing a picture here. Think about what's happening. So you have a kite flying in the sky. And again, obviously, picture doesn't have to be perfect. But you know, you have a little kite here flying in the sky, usually a little bow or string on it. And there's somebody over here. Obviously, if someone's flying a kite, there's going to be somebody standing on the ground, right, who's actually holding that kite string. And it's going to be attached to the kite. So, well, what do we know here? We know that the kite flies at a height of 30 feet, and we know that 65 feet of string is out. So this length here of the person holding the kite must be 65 feet. And is it a straight line? Now, straight line doesn't have to mean vertical or horizontal. It could be at a diagonal, right? If you're holding a kite, it's probably not directly above your head. It's probably at an angle. So this is the 65 feet right here. And then the height then, coming straight across, would be that 30 feet. Now, the height would be from, that's given here is implied from where you're holding it, right? Because usually you wouldn't be holding it like while laying flat on the ground, right? You're probably holding it a few feet off the ground. So you just want to be careful here that 30 feet would be in relation to this triangle that we're drawing here. So it may actually be a little taller in the sky. We're doing it based on how tall it is compared to you, how high above you. And we're looking to find that angle of elevation here, the angle it makes with the ground. So it would be this angle right here. All right, so let's see what we have here. So I need to find the angle. I know two of the sides. I could find the other one if I want to, but I know two sides. I know the opposite side and the hypotenuse here, right? Directly across on the 90-degree angle. So if you think about opposite and hypotenuse, well, what relates those two things? It would be sine, right? So sine of theta is equal to opposite over your hypotenuse. Now I don't know theta here, so sine of theta is equal to, in this case, 30 over 65. Now this one's a little bit different. We actually have seen this before in previous videos. And when you don't know the theta, you actually have to use an inverse function to solve. So this is kind of a nice little reminder here that to actually solve for that theta, you're going to use the inverse function. So if it's sine, we're going to use inverse sine. And then we're going to use that 30 over 65. You still want to make sure you're in the right mode. So on your calculator, again, just double check. Here we're using degrees. So make sure you're in degree mode. And I can see my inverse function right there for my inverse sine. So I'm going to press second and then sine to get that inverse function. 30 divided by 65. And I get about 27.486 degrees. And we do want to round to the nearest tenth, it said. So about 27.5 degrees. So just a nice little reminder here, if you don't have the angle, but you have the other two sides, you're going to use your inverse function on your calculator to solve for that angle. Okay, and I'm going to do one more example here before we move on to a different style. So again, using more right triangles in this case. All right, so I'm going to give you a little bit of background. I won't write every little detail down. So let's say you're taking your first hot air balloon ride and your friend is going to be there to video, the whole experience for you so that she can video you or he can video you from the ground level, whoever your friend is. So your friend is sitting on ground level and is sitting about 100 feet away from you from your point of launch, making a video of, the look on your face as you go up in this hot air balloon. Right, so let's draw our little friend in here. Okay. And that little friend is about 100 feet from you, and you're in your hot air balloon. So what happens is at one instant, that the angle of elevation from the video camera to your face is 31.7 degrees. It's 100 feet. So let's say you're going up a little bit in your hot air balloon here. And it's going to be a really bad drawing, but you guys, you get it, right? Here's your hot air balloon. And we're going up. And the angle of elevation here is going to be 31.7 degrees. Okay. And then what happens is the hot air balloon doesn't stop, right? It's going to keep going a little bit higher still. And let's say maybe 1 minute later, the angle of elevation is now 76.2 degrees. Okay, so that hot air balloon is going to keep going up. And what happens is you go a little bit higher now. And I use a different color here just to help show that. And now what's happening, so looking at kind of this triangle, is that your angle of elevation, I'll do that one in pink, is going to be 76.2 degrees. And that's the whole thing, not just the top part, right? The whole angle there. And let's say a minute has gone by. Okay, so it's been about a minute and you've gone up pretty quickly. So our question is, how far did you travel during that minute? So that's the question that we're looking at here. So we're really looking to find this piece, right? That's really what we're looking for. right? Because we were already a little bit high. And we're saying, okay, well, now we went up the next group. So maybe your friend's taking a picture and they took a picture at the 31-degree angle, and then they took another picture at the 76-degree angle or something like that. And you want to know the change in the height between the two. So how far higher did you go between those two? So we don't want the whole height necessarily. We just want the change between the heights. But to do that, we have a little bit of work here. So this is our most complicated one. But notice that I do have two triangles. So my first triangle, and I'm not going to draw them to scale, I'm just going to kind of draw them here, is you have that 100 feet and you have your angle of 31.7 degrees. And then for your other triangle, I'll just make it a little bit bigger. You have still 100 feet, but your angle here is 76.2 degrees. Within this picture. And then what's going to happen, I can find the height of both of these. And then what I can do is I can subtract the heights to get that change, right? If I know the height of the pink triangle and I know the height of the black triangle, I can subtract those two heights to get that blue value there. So that's what we're going to do. I'm going to find this height here. And then I'm also going to find this height here. And then I'll be able to subtract those two to get that blue change. So let's go ahead and do that. Think about what you need here. I know an angle. I'm looking for the opposite side and I have the adjacent. So this is all tangent stuff. So tangent of 31.7 degrees, again, it would be opposite over adjacent. So the height over 100. And here would be tangent of 76.2 degrees, again, opposite over adjacent. So you're looking at h over 100. And we're going to do a little bit of solving. So for the first case, I'm going to go ahead and multiply both sides by 100. And then I'm going to do the same thing in the second case. And then I'm going to go ahead, I'm going to use my calculator here. So for the first one, you can try this at home. Again, make sure you're in degrees. I'm going to round as well. When you multiply tangent 31.7 degrees by 100, you get about 61.8, and this would be in feet. And then for the other one, when you do that side, you get 407.1 foot, again, approximately. So now I know the two heights of the triangles, and what I can do is I can subtract them to get my final answer here. So 407.1 minus 61.8. And that change is going to give me about, let's see, 345.3. So how far did you change in that minute? Well, in that 1 minute, or between those two angle changes, you went up another 345 feet during that change. So that angle there makes quite a difference, right? If you look at it, it's a little over double, but the height changed significantly, right? It's not like just double the height. So you can see that, you know, the ratio is not linear like we're maybe used to, right? You have a much bigger change there with that change in elevation going from 31 to 76. So right triangles, again, are really one of the most common applications we see in trigonometry or with trig functions. They're not the only one, but they're a really, really common one. And they're used, you know, very frequently anytime also in like building construction, a lot of boat building as well.